Good morning, Stamina.
Morning.
Good morning. How are you today?
Good. I'm sorry, I'll be a Zoomie today.
Oh, no problem.
How are you? Did you have a good weekend?
I did, yes. Well, my walk was cancelled, but I made my own walk around the canals for around 6 miles, which was really interesting.
Yeah, canals are nice.
Yeah, I discovered a new circular walk. So circular walks are good, obviously, because they get you back where you started. You don't have to get a bus or anything like that.
That's nice.
Yeah. Did you do anything good?
I was working.
Oh, dear.
It was all right.
Yeah, I guess people are having some kind of Christmassy feel to work at the moment, aren't they? Slowly.
Yeah.
I used to like working in clubs and pubs and things at Christmas. It was good. It's like a big party most of the time.
Oh, well, until someone gets a bit too drunk.
Yeah, I'm afraid the English do that.
Yeah, have to do some
It's a
first
confidence thing. They can't really enjoy themselves unless they get drunk.
Oh, I don't know. Yeah.
Some people. I think we're here. I think we're in this one. Need to join the fun here. Got my microphone. Share my desktop. I think we're here. Put this in the chat.
Good morning.
Morning.
Stamina. I'm just going to be back. I'm just going to bring coffee.
Yep, sure.
Thank you.
Okay. Good morning, Ritu. Good morning, Fahima. Good morning, Maram. Already said good morning, Stamina. So yeah, lovely to see you all. Sitting here on my own in the dark with no roomies. I just want to plug in my power supply, which is the reason why I disappeared for a short while. Okay, that's better. So I hope we all had a lovely weekend. And let's begin. So I think we got as far as visualizing inputs and outputs. Let me just check. Create a machine learning model. Training and running your first model. Yes, we did this. And we did this. And we did inputs and outputs. We did inputs and outputs. And then we visualized it. And we got as far as, yeah, graphing our data. And we looked at how to use the model. And we went right on to the next model, which was all about Titanic. Real world use. Did the knowledge check. Radio on in the background. And then we did the summary. And then we've gone to other modules. Okay, no worries. Okay, so let's sure we've done the harness sizes. So let's go back and find modules. I think it's probably something like.
Hi, Steve. Steve, can you share your screen?
Oh, I thought I was. Sorry, did I not do that? Oh, no, I didn't. Oh, I did it on the other one, that's why. Okay, so I'm just going to find the right place for us. That's a good start, I think. This is the unit. Yeah, this is the one where we're starting today, I think, where we did this one. So let's carry on down here. Visualizing data with matplotlib, real world data, examining knowledge check summary. So we're now on to the next one.
Morning.
Good morning. 1 second. So we need to go to I think that was it. Okay, let's do it this way. Let's go back. Bookmarks. Find our think it's this one. That's a certificate, so that's one we've just finished. So I just need to get to one after that, which is
We were on the one explore and analyze data.
understanding data science, weren't we? Really, we were here, and we were in option 1, the complete course, and then we can look down to see. So we did build classical learning with supervised, introduction for data. I think that's what we've done. Trained and understood the model. No, regression is not what we're just trying to find the Titanic stuff, really. That here?
Just before that one.
Before that one, you think?
If you go up a bit.
Ah. That must be
The Titanic stuff is this one, introduction to
machine learning. Yeah, 45 minutes. Okay, excellent. So I think we finished that, didn't we? Let's have a look anyway.
Yeah.
So good, bad, missing data. Yeah, here we are. One hot vectors. Yeah, we looked at that for class, didn't we? Predicting knowledge check summary. So we are now here. If I just start this module. Yeah, this is what we haven't seen. So I'm just going to put this on the chat, so we all know where we're starting. So we're starting from today. There. So if we all get there, I'll see you there in 1 minute. Good morning, Said. Yeah, good to see you. Here's. You don't need the projector, do you? No. Okay. Okay, so that's where we are today. I use scikit-learn all the time. My applications don't involve deep learning because I don't really have enough samples to do that. So I haven't used TensorFlow yet or PyTorch. Scikit-learn I'm using all the time. In fact, scikit-learn has got some very good, it's got k-means as a standard output. And while you're reading that, my current task on my project is I have a distance matrix between 1,000 words spread in their usage over 1,254 questions. So I know the distance between each word based on their usage. What we then need to do is to look at the data in more detail, and we use something called Dijkstra's transform for that. That enables clusters that are very close together to stay together, but anything that's slightly outside the cluster to be re-examined for its real distance from the cluster. And then I can run k-means on that, and then take the error from k-means, the sum squared error, which is the inertia parameter from scikit-learn k-means, and use that to optimize the value of k. That's what I'm doing at the moment, this afternoon, in fact. And I have to present the results to Dr. Rice tomorrow. So that's what it says here. It all begins with analyzing the data, and that's absolutely true. Okay, so common data exploration and analysis tasks. We're going to be using NumPys, Pandas, and Matplotlib to analyze data. NumPys is all to do with numbers and calculations. Pandas is excellent in terms of array manipulation. For example, I was previously updating the 1 million cells in my data spreadsheet. I wrote a macro in Excel to do that, and it took 18 hours to run. I found a function on Saturday when I was working called pandas where, which enables you to say wherever there is a certain value, you can convert it into another value. And I'm going to run a test on it this afternoon, but I think it's going to be a lot faster than 18 hours. So let's see. So yeah, Pandas has got some brilliant functions, and Matplotlib, of course, is our standard graphing package, although we up until now have used a Python wrapper around Plotly called graphics, from which we've been using. But let's see what we use next. So we're going to explore data with NumPys and Pandas. Next unit. I'll let you read that for 3 minutes. Yeah, I'd agree with that. Pandas is like Excel for Python. It's exactly what I'm using it for. Already. Okay. I'll let you warm up by reading that. The idea of testing a hypothesis. Well, it's an iterative process, that's true, because what I'll be doing is running a loop, taking values of the diameter of my clusters from a 0.1 distance to a 0.5 distance in 0.02 distance steps. So that'll be 40 steps I shall be running it, and each one, for each step, I will find the optimum value of k based on the minimum sum squared error, so the optimum number of clusters for each setting. So the end result should be a nice graph showing what value of so-called E, which is the diameter of the clusters before Dijkstra does his stuff, to the minimum error. And of course, the point about the error is, the way to see it is this. If, say you've got 1,000, as I have 1,000 features, if I started off with 1,000 clusters and I put one feature in the middle of each cluster, my error would be 0, because they would all be at their centroid. However, that's not particularly useful in terms of clustering the data. So there has to be a certain configuration of the data that produces the overall sum minimum error. That's the total sum of every feature distance between a feature distance and the centroid of that cluster. And that's what we want to try and minimize when we're clustering. And that's what I'm trying to do with my current data set, is to find out the best value of k. Now, I know that it came from 8 different topic areas. So what should happen is that k should come out to be 8. But if there are hidden clusters within that topic area designation that are substantial, proper clusters, proper subdividing of the work, then it will find those. That's the plan anyway. Anyway, so that's what I'm doing this afternoon. So next unit, exercise, explore the data with NumPy and pandas. Let's do that. So I'm sure we're going to have to activate our sandbox, etc. Here goes. So let's start. Let's activate it and then see if we've got to do with our sandbox. 3, 2, 1. Just run the cell, and I'm sure you'll have to start your sandbox again. Yeah. Do I have to log in? No. Ooh, excellent. Okay, so what we've done here, we simply declared a list of data which we can then print. So if we do that, we'll just simply see it's a bit slow this morning for such a small amount of data. Less than 1 second. Yeah, I don't believe it. So there's the list. It's printed it out. Nice and straightforward. So the data has been loaded into a Python list structure, which is a good data type for general data manipulation. Yeah, it's true, but it's not optimized in any way. For that, we're going to need NumPy. So we can use convert this list into a NumPy array. Okay, so just simply we're importing NumPy as NP, as that's pretty standard. Grades we're saying is NumPy array of data, and we can print the grades, and we can see that it's got a little bit more structure. So that is all the fields, the commas have gone, and we could easily now access and manipulate all those points. I mean, because if you then just simply typed grades, because that was a NumPy array, we get the pretty version of it. There we go. So we get to see a bit more. We get to see all of the data, the absolute structure in here. So let's move on. So just in case you're wondering about the differences between a list and a NumPy array, let's compare how the data types behave when we use them expressions that multiply by 2. Okay, so with a NumPy array, we'll see the difference. So print type data times 2. So that's our comment, and then we just do data times 2 or grades times 2, and we'll see the difference. So what's happened with an NumPy array is that every element has been multiplied by 2, which I think is what we wanted to happen. Whereas in the list, all you've done is doubled the elements. Let's have a check on that. Yeah, we've just simply doubled the length. So when we times 2 of just a list, all we do is double the list. We just append. It's like appending itself. It's twice as long. Whereas we do a NumPy array, NumPy takes it as an operator, and it multiplies every element in this case by 2. So that's the difference. In order to start without a NumPy, you'd have to actually iterate through each element one at a time and then multiply them by 2 if you were just dealing with a straight list. But because we've got an array, a NumPy array, we can do clever stuff. So note the multiplying a list by 2 creates a new list twice the length, with the original sequences as list elements repeated. Multiplying a NumPy array, on the other hand, performs an element-wise calculation in which the array behaves like a vector. So we end up with an array of the same size, which each element has been multiplied by 2. Key takeaway from this is NumPy arrays are specifically designed to support mathematical operations on numeric data. which makes them more useful for data analysis than a generic list. Yeah, it's a real pain if you've got to do stuff on lists because it means you have to access every single element. You might have spotted that the class type for the NumPy array is a NumPy ND array. The ND indicates that this is a structure that consists of multiple dimensions. It can have n dimensions. Our specific instance has a single dimension of student grades. So, for example, if we were going to be using this to plot a 2D array, you would have one array for your X, one for your Y, and if it was a 3D, you'd have one for X, one for Y, and one for Z. The rules are for the plotting is that, of course, each array must have the same length. And quite often, you'll get the problem that they don't. And it throws it out and says, I can't plot it. Run the cell below to view the shape of our array. Shape, as I said before, is a very powerful idea. It's a very good diagnostic. It just gives you some idea what's going on. So grades is therefore a single dimensional 22 element structure. Okay. The dimensions would be here. If it had another dimension, it would be in there. But the default is single dimension. Shape confirms this only array has one dimension, which consists of 22 elements, 22 grades in the original list. You can access the individual elements in the array by their zero most ordinal position. Right, so just like when we were extracting the slope and the intercept, as in the parameters with a subscript 0 and a subscript 1, that's how you access the individual elements in the array. So you can actually, it's done by position starting from 0. Very important not to overrun, because that will chuck you an error out if you put in a number in there longer than the array is physically. And it's easy to forget that the array will start at 0. The first position is 0. So if ever you're counting through in some way, always remember that. So you know your way around an NumPy array now. Let's do some analysis on the grades data. You can apply aggregations across the elements in the array. Let's find a simple average grade. So grades.mean, a very powerful idea. Finds the average value. I mean, that's that would not be a, without that, that would be a 3 or 4 line procedure to do that. And does it all nicely in one go. So let's find that. That's the average. We didn't specify how many decimal places, so it's defaulted to its float value. So the mean grade is just around 50, more or less in the middle. Let's add a second set of data for the same students, this time recording the typical number of hours per week they devoted to studying. Okay, so it's very, very important that the number in these is also 22. So study hours is this. So we created another list. And then we're going to create a 2D array from both study hours and grades. Okay, so student data is an NP array and it's of 2 dimensions, and each of which is a list. So it's taking 2 lists and making a 2D NumPy array. And it's vital that those 2 are the same length. Let's see what happens if they're not. We'll do it properly first. If we can trip it up. And then it's just going to print out in the pretty format the student array. So there we go. So here's our first array, and here's the second one. Okay, so that's the first dimension, and that's the second dimension. That's how it works. The thing that separates the dimensions are obviously the square brackets here. That's the first list and the first dimension, comma, second list, and therefore the second dimension. And let's just for a moment remove that 0. That's 12.0, isn't it? Let's just take that out. And let's see what it does. It should say that they're of different lengths, so I can't do it. Yeah. So with different lengths or shapes is deprecated. If you meant to do this, you must specify when D-type object. So it will fill in a default value if it's not used. So let's put this back, comma 12.0, and then we run it again, and it should run. There we go. So yeah, not a good idea to have them at different lengths because its behavior is at best undefined. At worst, will get you into a lot of trouble. So we created our array. There's our student data there. Now we've got a two-dimensional array, an array of arrays. Let's look at its shape. And as we saw before, we saw it as 22, nothing. Now we've got 22 to 22. So we've got a list. Its dimension is 2 by 22. So 2 dimensions, each of 22. Okay, that's the way it works. To navigate this structure, you need to specify the possible position of each element in the hierarchy. So the first value in the first array, so we've now got 2 subscripts. The first one corresponds to, if you look at this, that's why shape is so useful. It tells you what you should use. So that 2 is the first value here. So that is the list position, the first element of the first element. There are 2 elements in total, 2 lists that were made up from. So 0, 0 is the first one of both. So if you like, if it was a square, that would be in the top left-hand corner. If your values of your array were put into a square, that will be your top left-hand corner value, 0, 0. So let's find it. It should be a single value. It's coming out at 10. Now let's see if we can see if that's right by looking at this. Well, we had 2 arrays. Here it is. So our top left-hand value is 10. There it is. And that's what we've seen here. Let's see if we can predict our bottom corner value. All right. What number are we going to put in for our bottom corner value? 1. Now be careful with a 0 start. Yeah, it's going to be 121, isn't it? Yeah, as I said before, always be careful that 0 start. It will trip you up, especially if you're reading things like it contains 22 elements. Very easy to put 22 in here. And it's the second of our elements. So this, let's make a prediction, should be 64. Yes? Let's see if we're right. There we go, 64. So what I want you to do is just to try one yourself, maybe somewhere in the middle, just so you understand what those subscripts are. So pick a value, not necessarily a corner value, and satisfy yourself that you understand how these 2 subscripts worked. Okay, I'll let you do that for a minute. A very important skill. Okay. I think we're all happy with that. Can we have a quick hands up to say that we're all happy with how to operate subscripts on NumPy arrays made from lists? Okay, hands down. Let's move on then. So what we can do is to apply this idea of dot mean to each subarray. So we can apply it to a single array, a two-dimensional array, or in this case, we can use our index here to say that's our first element of our 2D array, so the first dimension, and second one here. So the first dimension, remember, was to do with the study, and the second one was to do with the grade. So study hours against grade, and we can then print this. Quite useful, and we'll explain how it works. So we've got study hours 10.52, average grade 49.18. So let's see what this print statement does. So the print statement gives us average study hours. So that's in our literal here, what we're going to print. And then we have got this formatting here, which means that we've got a parameter coming in, a value here, and the format is of 2 decimal places, I think. Yeah, 2 decimal places, and average grade here. Format average grade, comma, average study. Yeah, we're just referring back to the format again. So that's how you would print something like that out. So we're going to explore tabular data with pandas. NumPy provides a lot of the functionality you need to work with numbers, specifically arrays of number values. When you start to deal with two-dimensional tables of data, the pandas package offers a more convenient structure to work. And this is our so-called data frame. Now, all along, we've been using data frames for pretty much everything we've done so far. So we're going to make a data frame of, now this is what this is going to say. These names are going to be our columns, and the study hours, which is going to be our first row, is student data 0, and our second row, which is grades, will be our student data 1. So let's have a real investigation of this, because this is an important transformation that you will do many times. Associating labels with the data is very important, because if you're printing out, I don't know, say a clustering, you don't want just dumb circles for your data point. You would really like those labels to be your data points. And so it's important to understand how they're related within a data frame, because once we've got that, it's possible to extract just the labels, for example, once you've got it in that format. So DF students is a Panda data frame, which we put in this format, and then we print it off at the end, and it will look quite pretty, I think. There we go. So these are our, oh, it's the other way around. So they've done these as the first column, and then this one as a column, and then this one as a column, and then this one as a number, just to access it. This number is automatically labeled. Obviously, you can transform it in any way you wish. But in this case, this is the first named column, which is here. Name refers to the first column, and then study hours refers to the second column, and it's our data that we've got. And lastly, the third column is student data, which is, student data 1, which is the grade that they got. So now we can do some serious regression. Obviously, the name is irrelevant in terms of doing any kind of regression, but we can predict the grade from the study hours. We might be able to get a regression line for that. So that's the format. Panda arrays, column, column, column. And then this index is done automatically for us when we're printing. So let's move on. In addition to the columns you specify, the data frame includes an index to uniquely identify each row. We could have specified the index explicitly and assigned it any kind of appropriate value, for example, an email address, but because we didn't specify an index, one has been created with a unique integer for each row. Yep. You can use the data forms lock method to retrieve data for a specific index value. So dfstudent.lock5, so that's location. Let's see what that gets us. So location 5 is Vicky, student hours 1, grade 3. So location refers to the index here. Okay, so if you put in lock 5, it finds the 5th, or the one that's labelled, given the index 5, and gives it in a nice pretty format of Vicky. So it's almost like it's retrieving a record whose name's Vicky, and this is her data. We can also get the data at a range of index values. So we can look at the first 6, for example. 0, 1, 2, 3, 4, and 5. We get a nice chunk of the chart there. Very, very simple operation to do something that would, if you try to do that specifically in code, would be a bit more complicated. In addition to being able to use the lock method to find rows based on the index, you can use the ILOC to find the rows based on their ordinal position in the data frame, regardless of the index. So if we've got get data in the first 5 rows, DF students lock 05, ILOC 05. So how have they done this ordinally? Dan, Joanne, Pedro, Rosie, Ethan. Okay, so it's a little slightly confusing in that the in this case, the ordinal position is very, very similar to the index, apart from the first 5 in their ordinal position. So it's very similar to this. It doesn't have to be, because if these were different values, then they could be ordered differently. But in that particular case, it returns that. And compare them to the results you obtained. Can you spot the difference? The lock method returned rows with an index label in the list 0 to 5, which is 0, 4, and 5, 6 rows. However, the ILOC method returns the rows in the positions indicated. So basically, whatever numbers were in here, if these were the first 5 positions, then they would be sent. So if this was emails, for example, obviously the first 5 positions would just be the first 5 positions in the graph. It wouldn't be looking at the indexes in any way. So ILOC identifies data values in a data frame by position, which extends beyond rows into columns. So for example, you can use it to find the values of the columns in positions in 1 and 2 in row 0, like this. So what we found is ILOC 012. So what we're looking for is in the first row. We don't know who that is. We don't care who it is. We're not looking at the name. We're only looking, saying, in our first row, what data do we have? And we have 1 and 2. So that is going to be for this. So it's specifying which columns to use. So for index 0, which means the first row, we want the first 2 columns of data. And that's what we've got, study hours 10 and grade 50. So that's these two, that point and that point there. Notice Dan hasn't been specified. It's been done by iLocation, which is that point there. Okay, let's return to the lock method and see how it works with columns. Remember that lock is used to locate data based on an index rather than positions. In the absence of an explicit index column, the rows are indexed as integer values, but the columns are identified by name. So let's see what we can work out here. df students dot lock, so that means by index, so that's the first one. For grade, and the values we'll get back then is we can access a specific point in the row. We're able to access that point. So by giving it index, this number here, not position, index is 0, and we retrieve the grade. So we can actually access any point by name there, which is quite a powerful idea. Accessing data by giving it the column name. It's almost a data indirection, a content addressable memory, we used to call them. Here's another useful trick. Let's just run it anyway. Here we did that. You can use the lock method to find index rows based on a filtering expression that references named columns other than the index, like this. This is interesting. So df students lock df of students for name equal to Aisha. Okay, so this is our condition here. So we would expect to see effectively extract the row of, in the situation where the location in df students where name equals Aisha. So what we're going to get is Aisha's record, which is, okay, she's not in that list, so she's in the bigger list. Let's see where it is, probably around 22 or something, but let's find it. Because at the moment she's not in the top 5. Is she? I guess she might be 22. So there you go, she is 21, and it's just recovered her grade in a very nice way. And obviously once we've got that, we can do further operations on it. We can play around with that because that's a nice easy row to begin with. And of course df students lock, and you can then make something equal to something and then be able to extract that piece of information. Actually, you don't need to specify the use of a lock method. You can simply apply a data frame filtering expression like this. df students, find the df student for which name is equal to Aisha. That's the simplest way to use that, and you get the same result. Okay, for good measure, you can achieve the same results by using the data frames query method. So this is when it's looking at it like it's a database. df students plant the query for name equals Aisha, and it will return the same value. So that's using it like it's a database, and you're putting in a key, a filter, The three previous examples underline occasionally confusing truths about working with pandas. Often there are multiple ways to achieve the same results. Yes, I'd stick with one that works for you. Another example is the way you refer to the data frame column name. You can specify the column name as a named index value, as in DF student's name, examples we've seen so far, or you can use the column as a property like this, which is what we've done. DF students dot name. So we're just referring, I quite like this. This is the way I would use it. DF students of DF students dot name, because this is kind of more of an object oriented kind of approach here, which is very, very common throughout the rest of Python. So rather than play around with iloc and lock and all that sort of stuff, just go straight into the field, I think, and get whatever you need. And of course, this is a nice, easy test to implement and explore in your data. You get the same thing. 2 specific skills you need to have without any question, and that is loading in here. Loading a data frame from a file. So this is our file, and you can see that it's going to be our grades.csv file and DF students. So we're going to create a NumPy array from reading, or no, we just array it for the moment, reading CSV. So that's what it returns. Delimiter is a column, which makes it why it's a comma separated value file, and header is to infer. So I think that's going to be that it should look at the data itself and try and work out if the format of the data, the format of the header, is the same as the format as the rest. So if the format of the header row is letters, for names or labels, that is going to be different to the format of the rest of the rows. So it's going to infer from the comparison between the data and the header what it should do, and then we can just print the head, and let's see how it's inferred it. So we printed the first 5 rows, and it's obviously inferred that this is not data. This is header, and that's what it means. It's basically said to itself, this stuff is numbers. Okay, that's some letters in there, but this clearly are headers, are labels. So that's why it's not tried to interpret these as anything else other than the first row as being the header. Again, head just gives you the first 5. So we shouldn't be surprised at that. We've now read it from, and we can manipulate it just as before. And looking again, handling missing values. Well, let's see if there are any using the isNull method. So it's looking to see if there's any null values. Yeah, there's 2 missing values here. Of course, they will be insufficient to review all the rows and the columns individually, so you can get the sum of the missing values in each column using the .sum property of isNull, and that will be much easier to see. And we can see that we've got 1 in the study hours and 2's in the grades. So that's what's missing. So now we know that there's 1 missing in study hours value and 2 missing in the grade values. To see them in context, we can filter the data frame, consider only the rows where they're null, and this is DF students. If DF students is null.any, access equals 1. Let's think about this. Of the columns, access 1 of the data frame. Okay. So let's go into this. Okay, so this is axis 1, that's columns. What's I assume row is 0. Let's have a look. Axis type Boolean. Any axis, Boolean only, Boolean none, level none, args. No, it can actually take a range or even a series. So we're just saying that in this one, axis 1 of a data frame's null. Hang on, let's just Google it. NumPy. No, it's referring, one is referring to columns, I think, but let's see. NumPy, hang on. Oops. Sorry. Is null.any, that's what I'm looking for. No, it is nan, it is null. Hang on. Yeah, there we go. So this is any axis. Axis or axis along which a logical OR reduction is performed. So it's checking, that's the column then. Yeah, what value is it going to take? Axis may be negative, in which case it counts from the last to the first axis. Okay, let's go for an example, which is further down. Examples is any, is any, is any. Still not clear about that. If this is a tuple event, a reduction performed on multiple axis instead of single axis. Okay, so I think we're going to just settle that it's 1, and it might be clearer precisely what that means. Oh, it can be none. So this is all the dimensions of the input array, which a logical OR. So yeah, that's the column, isn't it? We're doing a logical OR of all the rows in the column for is null. So this is for all columns, basically. That's what we're doing it for here. So do is null for all columns, and so it should find that grade is NaN here and here, and study hours is NaN there. So that finds everything, any across all columns. Axis equals 1 is all columns. That makes sense. So see what 2 does. 0 might be rows, of course. Whoops. See what happens. Doesn't like that. A Boolean series. Okay. Let's see if it handles that.
I think, Steve, it could run like, you know, in Oracle.
No, I think axis equals 1 means all columns. Otherwise, you've got to. Anyway, there they go. Let's move on. Sure, it will become absolutely clear what it is. When a data frame is retrieved, the missing numeric values show up as nan or not a number. So now we have found the null values. What can we do about them? One common approach is to impute replacement values. If the number of study hours is missing, we could just assume that the student studied for an average length of time and replace the missing value with the mean study hours. To do this, we can use the fill NA method. Here we go. dfstudents.study hours is dfstudents.study hours fill NA with dfstudents.study hours mean, and then return dfstudents. It looks pretty straightforward, doesn't it? Using a fill NA method. And there we go. So if we now run our previous method, we'll find that there are no longer any empty rows, although there are. That's study hours. I now need to do the same thing on grade, don't we? We need to do the same thing on grade. So let's modify this to do the same thing on the grade. df.grade. Oh, what is it called? It's what's our grade field called? So what I want you to do is to find out what the correct field is for grade and change that expression. Sorry, not that expression, and not that one. Oh no, we're going to come on to that anyway. So we are now here, but we've still got a couple of grade information. Alternately, it might be important to ensure you only use data you know to be correct. So you can drop rows or columns that contains null values using the drop NA method. So this is kind of what we did before when we manually removed the rows that had there you go. Axis 0 is the rows. So axis 1 is the columns and axis 0 is the rows. So df students equals df drop NA for axis equals 0, which is the rows, of any. So it's saying, let's have a look at what's precisely what any means. What that method is, parameter. Should look at the drop NA method. And so this will remove the row. And if we go to the bottom here, we will see our NA grades have now been removed because the row has been removed. So we've only got, oh, it didn't remove the row because we've still got 22. Okay, let's go. Oh, I see. Oh, Bill and Ted. Yeah, we added Bill and Ted. Did we miss that then? Yeah, I jumped ahead, didn't I? True. Loading a data frame from a file, did that. Handling missing values, did that. Saw those, saw that. There we go, that's Bill and Ted. So where do we add Bill and Ted? Oh, Bill and Ted was in the file. Yeah, I got it. So we didn't add it manually. And now we're just taking Bill and Ted out because they had a missing grade. I understand that now. Students mean, okay, let's go here. Yeah, we did that, we did that, we did that. And we didn't do that. Didn't do anything on passing grade. So we're here. We've taken out Bill and Ted because they had a null value. Okay. So now we've cleaned the missing values. We're ready to explore the data in the data frame. Let's start by comparing the mean study hours and grades. So get the mean study hours using the column name as the index. There's our column name, mean study. So we should be able to get that value, get the mean grade using the column name as property, just like before. So we're going to find the mean grade is the students.grade mean, and print the mean study hours and the mean grade. So print it in this nice pretty format using a couple of decimal places, and apply that format to mean study and mean grade. So this is a pretty standard print statement to do that kind of thing. And we've got the average weekly study hours 10.52, so 2 decimal places there, and the average grade 49.18. So we've covered that information. So let's filter the data frame to find only the students who studied for more than the average amount of time. So what we're going to do now is to apply a filter. So DF students of DF students.study hours greater than mean study. So this is a filter, or a mask, in fact. This is a mask that's applied to DF students. So only DF students that where their study hours are greater than the mean study hours are returned. And something important to notice here. Jumping out of handling missing values. Bill and Ted, exploring the data. Then we've got the mean grade. Let's assume the pass grade is, so start that again. Oops. So that was asking that the filtered result is itself a data frame. You can work with its columns just like any other data frame. Let's find the average grade for students who undertook more than the average grade amount of time. So there we go. We can say find the grade mean of the students that have applied to this filter. So we get one result coming there. So as you can see, very, very powerful constructs. Let's try the next one. Let's assume the passing grade is 60. We can use the information to add a new column to the data frame, indicating whether or not each student passed. So we need to create a series containing the passing failed indicator, and then we'll concatenate that series as a new column. Axis 1 is columns. So here goes. Passes is a new pandas series containing the pass-fail indicator, and then we'll concatenate that series as a new column. So firstly, we're going to make a series which is pd.series of DF students grade greater or equal to 60, and then DF students, which is the original, is pandas concatenate, so that means add to the end, DF students passes dot rename pass axis 1. So renaming a column, a new column, axis 1 is this column, so basically adding a column and then printing it out again. So we should just end up with another column with pass fail. There it is. So if you wanted to add a column, definitely use that. It's a nice tidy little construct there, and we'll end up with that. And I think go down again. It's jumping up, I don't like that. So we're pretty close. Contain the pass fail, we've got that. And then lastly, we can use the group by method to group the student data into groups based on the pass column that you added previously. So print dfstudents.group by dfstudents.pass.name count. So what's that going to do? How many students passed and failed? Okay. If we run that, we'll see on the pass we have 15, and 7. So that's quite a nice construct as well to actually number. This group by will give us these two numbers. And then you can aggregate multiple fields in a group using available aggregation functions. You can find the mean study time and the mean grade time for the groups who passed and failed the course. That's quite a nice construct. And there it goes. And lastly today, or lastly this morning, we can make it easier to manipulate data. Let's have a look, see what this one does. This is doing a sort, and there we go. We've sorted everyone by grade and obviously whether they passed. Clearly, if you got more than 60, you passed, which was the characteristic was 60, wasn't it? So if you got more than 60, so that worked for that, and it orders the rest of them based on their grade. And I think we are done on that bit. So let's visualize the data after a 20-minute break. Represent the data visually. So that's where we're going to be when we come back in 20 minutes. Okay, see you then. Okay, we're back. So let's look at visualizing data still and representing data visually. All that stuff with the NumPy arrays and everything, as I was saying to Zayed, is it's a really powerful kind of cookbook for you to look back on and see a particular application of being able to grab a column or grab a value within a column or a row or group them or apply a mask in order to extract the data. It's quite a nice little set of usages for the functions there, and I shall certainly use them in the future because normally I don't access them in such an elegant way. I tend to iterate through the rows to get what data I need based on the structure I know that's there. But this is a far more powerful idea. So the next topic is huge. It's absolutely huge. It's about representing your data given, in this case, 2 or 3 dimensions. You won't normally try and visualize it in more than that number of dimensions. If you do, you will have to use some kind of dimension reduction scheme, again, which is a huge area of research, to convert multi-dimensional, and I mean up to 1,000 dimensions or more, reducing that down to something that you can visualize. And you can generally only visualize 2 or 3 dimensions. Or you can visualize 1 dimension. It's just points on a line, on a line with an equal other axis. So the line of y equals 1, all your values of x are in fact in 1 dimension, even though they are x, y in nature, so two dimensions. But if you fix 1 dimension and make it a line, then you can then just be looking at 1D, which would be represented as a simple list in Python. A list of those values would be represented as 1 dimension. And the double that we saw and we did, that could be seen as 2 dimensions. So location X and location Y are our 2 dimensions. So representing data visually means graphing it. This is done to provide fast qualitative assessment of our data. Important that qualitative means without too much concern for the numbers, but you're more concerned with the shape. Okay? Of course, you can extract quantitative data from a graph using other functions, which can be useful for understanding the results, finding outlier values, understanding how numbers are distributed, and so on. Or sometimes we know ahead of time what kind of graph will be more useful. Other times we use graphs in an exploratory way, yes, as I'm doing at the moment. To understand the power of data visualization, consider the data below. The location XY of a self-driving car in its raw form. It's hard to see any real patterns. The mean or average tell us that its path was centered around x equals 0.2 and y equals 0.3. So you've got to imagine this is the location of a car that's apparently driving randomly round a dot, a center with an x value 0.2 and a y value 0.3. So that's its center. So imagine it's doing donuts around that center. Okay. These are the values it can have. These are absolute values. And that's what you get if you plot that curve. If there's anything we can do for that. If you plot that graph, you will see that its location at any point is here. So it's, again, it doesn't really show much of a pattern. If we graph x versus y, we end up with a map. Okay, so that's location x and time. So that's its time. So in terms of seconds, where it was, its x location, how far away over time. And you could do the same thing in y. So for example, that would be if you started in the middle of a field or a concrete, like an airstrip, anywhere there was concrete, a car could drive around. Over time, that would be how far away you was from that point. So let's say in a positive X direction, you might therefore be, if you're in the middle of an airstrip, in the positive direction, X direction, you might find the takeoff point, and in the negative direction, you might find the communications tower, and the point where you're driving around on the airstrip will be in between that. It only shows your X location, so how far, literally how far away you are from your starting point. However, if you graph X versus Y, we get the location of the vehicle, and you can see that it's actually driving in quite a nice circle. So if you only consider one direction, let's try and do that. There's no time here, remember, there's no time. This is purely location where the car is driven. It's instantly obvious that the car has been driving in a circle, but at some point drove to the center of that circle. So obviously that's where it started, at the center, and at some point it went back to the center, which was here. Okay, that's where it went back to the center. Bear in mind we're only looking at the X here. And if we can predict it, let's predict it where it started. Starting point was definitely at X location, so a 0. So at some point it started here, and then it went a long way up to nearly 2 on the X location. So if we go to where it was nearly 2, so probably if we showed it in much finer time, we would see its track, but it's probably around here, almost 2 all the way around. So you can visualize the change in X. So the change in X from here, for example, went from very positive to very negative in a short time. So where could that be? Well, if it went from positive to negative in a short time, we can see that that would have been this path, because the X is positive here, negative there. So if in our graph, the X went from almost 2 to almost -2 in a short period, we would have to say that is most likely to be because the change is occurring quite fast. So it's in a short period. We've got lots of dots there. Each dot here, obviously, we've got a few of them here. Now, if a few dots have come in a certain amount of time, that means we'll be going quite slowly here. This is going quite slowly. So we went from a positive X to a negative X quite quickly. So I think probably you're talking here. There's a positive X. There is a negative X. You haven't got many data points in there, which means you were going quite fast. So my guess is that's what happened, which means that we started here and went there and then started this. Because that kind of makes sense, because we started there and went almost to 2, which would have been that point there. So that's probably where we started, and then we went like this. And towards the end, we slowed down. Let's see if we can prove that. Towards the end, as you can see, we haven't gone as far when we came back towards the end. So the end point here. So here was the point we crossed the 0, and we ended up with +2. So we ended up with, on the X, back to where we started. So it was +2 twice, there and there. And at the end, it was much slower. So you can interpret the graph, but matplotlib is much better for it. So the graphs aren't limited to 2D. It could be, you can explore all types of data, pie charts, stack bar graphs, spread, whiskograms, boxes, whisker plots, all sorts of other good stuff. So let's visualize data with matplotlib. It's a standard library. We might have to activate a new sandbox here. Sandbox activated. So as before, we're going to apply basic techniques to analyze data with basic statistics and visualizing using graphs. Okay, so load our data up, header infer as before. Let's just see if it's the same one. Yeah, it's the grades for the students. And we did all this stuff before. And we get the result. Three seconds. And this is basically where we left off before with Ted and What's It Gone, whether they passed or failed, grade, study hours, that's where we're starting from. Now, we've got some nice clean data. We've got a lovely true false column we can use, and we can start thinking about plotting it. So data frames provide a great way to explore and analyze and tabular data, but sometimes a picture is worth 1,000 rows and columns. It's true. The matplotlib library provides a foundation for plotting data visualizations and can greatly enhance your ability to analyze the data. So we're going to have a simple bar chart that shows the grade of each subject, of each student. So ensure matplotlibs are displayed in line with Notebook. So basically, this is a scaling thing in terms of the graphs you're going to plot. What you don't want to do is if you, and I've seen lots of error codes that have been brought up and people that have sent in things into chat boards and whatever, that they can't get their matplotlib graphs to be centered on the page. They're always to the left or to the right or cover the whole lot. They're too big. And this inline function just simply says, look, your text is normally this size wide. You get normally this many lines on a page, and basically this is what would look a nice, sensible size for your plot. So that's all it's doing. It's telling matplotlib to be sensible. So we're going to import pyplot as plot. So from now on, we can actually refer it just as PLT. And a bar graph then of name versus grade. So plot a bar graph where the X is the DF student's name, the dfstudents.name, and the height is dfstudents.grade. Okay, so this is a bar graph, which of course is going to have names in the x-axis, and the height of the bar graphs is their grade. So that and plot show is the last comment you do when you're using matplotlib, and that's when it shows on the screen. Up until now, up until just plot.bar, you wouldn't see anything visible. So at the end, you must always type in plot show, because that will plot the X and Y values that you've come up with. And of course, in this case, it's a bar graph. So your X values are categories, they're names, and the value is categorical, it's a name, and you've got height as being the grade. And this is what we see. Nice, pretty bar graph or bar plot. There we go. So, and again, it's not very tidy. The names have overwritten each other because of the size of the text. I have that problem all the time because I'm trying to label my diagrams with 1,000 words, and they just all overwrite each other. So, but what happens is that this has been put in line with the size of your notebook, sensible for your size of your notebook, which unfortunately means all your words are all written over each other. If you made this much bigger, you would be able to have it so that these names weren't overwriting. Oh yeah, that's one way of doing it. Yeah. So you have a sideways bar graph. Yeah. You always find fixes like that in Stack Overflow. What can I do when my graph is too big? Turn it on its side. Technically, it's not a bar. It's slightly tougher to read in that situation. But yeah, I'd agree with that. In fact, let's do that, shall we? Let's just for a bit of fun. Let's do this. Let's do. If we put in y equals student's name, let's see what happens. No, I didn't like that. It's not as simple as that. So we can't do that. So what we're going to have to do, I'm sure there's a rotate function somewhere. Do you want to put that? Have you got it? Can you put it in the chat? It's in the chat, is it? Okay, let's try that, everyone. Let's try this. This could be fun. Plot x ticks rotation 90. Oh, okay. Excellent. Let's grab that then. And let's put that in. Whoops. Whoops, not Python. So in here, so I assume we do before here, yeah? Oh, before plot show. Plot dot x ticks rotate 90. Let's see what happens. Yeah. So it's turn the labels around 90 degrees. Oh, I see what you mean. I thought you meant plot it on its side. So that the one, well, that's why I said swap it over to Y. I thought it was, yeah, okay. That's a really useful one, that one, isn't it? Plot x ticks rotation 90 degrees. Now we can clearly see our labels here. I think that's really nice. Yes, I think that's an excellent piece of work. That worked, but the chart could use some improvements to make it clearer to what we're looking at. Note to use PyPlot class. Plot the chart. The class provides a whole bunch of ways to improve the visual elements of a topic. For example, specifies the color, adds a title to the chart, add labels, adds a grid, and then rotate. Ah, there you go. They did it as well. No, it's great that we discovered it first. Plot ticks rotation equals 90. There it is. And plot grid color and so on. So that's the best way to learn anything, is to find it out for yourself. Look at that. That is pretty. So we put a nice little grid there, some rulers in, lots of numbers. We turned them around. It looks really pretty. Again, use this as a kind of cookbook for the future to make your plots look really nice. It looks pretty straightforward as being able to plot some nice bar graphs. So a plot is technically contained within a figure, as in the previous examples. The figure is created implicitly for you, but you can create it explicitly. Creates a figure with a specific size. And a nice thing about the figure is that then you can do save figure and as a PDF. That's the nice thing about when it's a figure. So there we go. Show the figure, plot show. So we create a figure. Figure equals plot, figure, flag size, so on. There it is. So this is the size of the dimensions of the figure in terms of units on the page. And we've got the bar graph, we can do the plot, the grade, we can do the rotation and show it. And now we get it nicely spaced across the page. Let's change the size a bit, make this 9 and make this 4. See what we get. Should still fit, hopefully. Yeah, okay, so it's looking a bit better, isn't it? So you can adjust that to be whatever fits on your page. And then once you save it, you can then import it into LaTeX or whatever you're using for your academic paper writing or whatever document you're producing. You can just import that figure then straight into your Word doc, whatever you like. So yeah, there it is. Looking good. And let's move on. These are really useful things to do, and having it as a code book, as a cookbook for you to look back on when you come to need to write these kind of functions is really nice. So 2 subplots, 1 row, 2 columns. So figure, so AX, which is our variable, plot dot subplots 1, 2, figure size 10, 4. So that's the size, and we're going to do it for create a bar plot versus grade on the first axis. So AX.0. So this is using AX.0. This is the information bar height as we set before, color orange, grades. Set the tick labels to be rotated by 90 degrees, as we know. Create a nice pie chart as well. But this time, this is on the second axis. So AX1. And then add a title. And this is what we get. So there we go. First one we've got for grades, and then for passing grades. Quite a nice presentation there, isn't it, side by side? So that's something that we can play with a lot to get different kinds of graphs. It gets a little bit heavy now with some of the statistical analysis we're going to have to do. So we're going to go through it. We went through the plotting fairly quickly because I thought it was completely intuitive. And you could always go back and see in detail how each little part was done. But we're not going to go so fast now through the analysis because these are, again, quite important concepts. So we've used methods and matplotlib to object to plot charts. However, matplotlib is so foundational to graphics in Python that many packages, including pandas, provide methods that abstract the underlying matplotlib functions and simplify the plotting. For example, the data frame provides its own methods for plotting data, as shown in the following example to plot a bar chart of study hours. So, dfstudents.plot.bar. So there we go. dfstudents is our array, and it has a function of plot, and it has a function of bar graph, and you just have to give it the names. And the y is the study hours, and color teal. And the figure size is 6 by 4 units. Let's have a look, see what that looks like. So here we've got our name against study hours. So it's an XY bar plot here of study hours, and the caption is for taking the default, which is for study hours. Because study hours is just what these bars actually mean. The bars actually mean the y-axis. The bars don't mean the labels, they mean the study hours. So it's taken the y-axis as our label. We can prove that by just doing this. Nope, can't find that because it needs to be H to exist. So it's definitely taking the real data. And I think that's all we can do. Yep. So getting started with statistical analysis. So now you know how to use Python to manipulate and visualize data. You can start analyzing it. A lot of data science is rooted in statistics. So we'll explore some basic statistical techniques. Note, this is not intended to teach you statistics, as that's a huge topic for a notebook. But some of the statistical concepts and techniques that we use as they explore data in the preparation for machine learning modeling. So we know what kind of models to apply. Unless you know your shape of your data and the characteristics of your data, then you won't know which model to apply. So when examining a variable, for example, student grades, data scientists are particularly interested in its distribution. In other words, how are different grades spread across the sample. The starting point for this exploration is often to visualize the data as a histogram to see how frequently each value of the variable occurs. Yeah, we call this the term frequency, is to see how often each value appears. So we can see what the most common grade is and all that kind of stuff. So we get the variable we're going to look at. Variable data is DF students of grade. So that's var data in this case. We're going to create a figure, is plot figure of the whole thing. So we must have predefined figure. Yes, we did. Plot the histogram of our var data. There it is. And add the titles and labels. Okay, Y label is frequency, value, data distribution, and then fig show. Let's see how we go. There it is. So we can see here how often it occurs, so-called the frequency, and the value. So this is, if you like, the distribution of the grades, this is the score that they got. Not whether they passed or failed, but the score. In fact, anyone above 60 passed, that's this region, and everyone below 60 failed. Now, what happens is, for example, whenever I used to run tests in schools that I was running, we had to fix the grade boundaries that the students would have to achieve in order to get to the different levels of either level 5, level 6, level 7, level 8, or even level 9 in the extreme case. And we were using that a certain percentage of students should get each of the grades. That was the idea. And the grade boundaries were therefore adjusted after the students have done the exam. Now, I always thought, no, that's a very poor way of doing it, but that's what the examination boards do. So every student that competes gets the grade boundary based on what produces the predicted number in each of the grades. And this is precisely the technique that is used to be able to find what those grade boundaries should be. Using exactly this. So the histogram for grades is a symmetric shape, while the most frequently occurring tends to be in the middle, the range around 50, with fewer grades at the extreme ends of the scale. So this is a central tendency issue. To understand the distribution better, we can examine the so-called measures of central tendency. which is a fancy way of describing statistics that represent the middle of the data. The goal of this is to try and find a typical value, because what then you can do once you've found your typical value is that you can shift your boundaries either side of that typical value, and then from that you can create absolute values which you can give to the students so that when they mark their tests, if they mark their tests, they can award themselves the correct grade. So the mean, a simple average based on adding, I'm not going to explain that. The median is the value in the middle of all of the sample values. So what you need to do to find the middle value and the median is you must put them in order, number order, and find the middle value. And if there are an even number of elements, you need to find the mean of the middle two values. That is your median. The mode is simply the most commonly occurring number. Mode as in fashion, as in a la mode, as it comes. The most normal, usual value is your mode, the most common mode. Occurring value in the sample set. Let's calculate these values along with the minimum and maximum values for comparison and show them on the histogram. Minimum and maximum values are important. Usually when deciding the grades, what I normally do is actually discard the top 10% and the bottom 10% of the grades as being outliers, and then zoom in on that middle 80, and that's where I work out all the grade boundaries that are used for the students. Let's see if they do that. Along with the maximum and minimum, of course, some sample sets there may be a tie for the most common value, in which case the data set is described as bimodal or even multimodal. Okay. So just grabbing the grade, we've done that. And then we're going to get some statistics. Min value is var min. So var, remember, is our grade. And grade is a number, not pass fail. So we can find the minimum, the maximum, the mean, the median, and the mode. They're our four values. And if mode, because mode may well end up with having more than one value. So for example, if there are two students that got 60 and also two students that got 65 and only one student that got all of the other grades, then that is bimodal. So you would then have to handle both of those. You can't. And the way you handle both of those is you put them in as subscripts in the mode data construct. So mode 0 will be the first element in mode. If you're pretty certain that is only going to be one, then just always use mode 0, because that will pull out the first one. But it's worthwhile investigating if mode 1 and mode 2 exist, because they might. And then print the minimum in 2 decimal place format with a backslash each time, so on a new line, median, mode, maximum, and apply that format to those 4 variables. So basically we should end up with minimum in double format, double decimal format, the actual value of the minimum, and then the mean, the median, and the mode. So this is the format here, and you have to apply that format to these variables. Okay, that's how it works in that order. That's what that's telling you to do. Let's make sure I'm in the right side of the sandbox. Yep. Okay, so we can create a figure from that. So figure equals plot the figure, fig size is that, plot the histogram, add the lines for each of our statistics. Well, I'm not going to go into detail on this because I think it's pretty obvious that you're going to be doing the min, the median, the mode, in the max and the mean in different colors. Got lovely colors here, all the same line style and all with the same line width. Okay, so we should see a really nice plot title there, plot X label, plot Y label, and then show, figure show. So here goes. We should get a really nice, oops. Must be down a bit then. Now it looks like minimum, mean, median, mode, maximum. So these are our minimum. These are our maximum values. And this you can see, because the median, the mean, and the mode are all pretty much in the same place, it tells you you've got quite a balanced data set. Now, if the average, the most common value, and the median value when they're put in order is all the same, pretty much, then you've got a very well behaved data set here. So we've got 49, 49.5, and 50, pretty much centered around that. And also that the minimum is 3, maximum is 97, so the span is about 94, and that is approximately twice. So it's pretty much centered. For the grey data, the mean it seems to be more or less in the middle. Another way to visualize the distributed variable is to use a box plot, sometimes called a box and whiskers plot. Let's create one. So we saw one of these before. We're looking at grade again. There's our figure. That's what we're going to plot. That's what we're going to describe. And then we're going to do a box plot of our variable, which is grade, add the titles and the labels, and show the figure. The box plot shows the distribution of the grade values in a different format. The box part of the plot shows where the inner 2 quartiles of the data reside. So that's quite important, because then outside of that, that's where you're going to find your outliers. So in this case, half the grades are between approximately 36 and 63. The whiskers extending from the box show the outer 2 quartiles. So the other half of the grades in this case are between 36 and 63, sorry, 0 and 36, or 63 and 100. The line in the box indicates the median. For learning, it can be useful to combine histograms and box plots, with the box plot's orientation changed to align it with the histogram. Okay, let's see what that looks like. So here is our box plot. So our first 2 quartiles, middle 2 quartiles are in this range, and then the bottom one is over here and over here. Now, if that wasn't a well-balanced data set, this box could be shifted up towards one end or the other one. And if that happens for your data, then you'd need to transform it in some way to try and get it back so that it was in the middle again. So we can create a function that we can reuse. So this is, as I said before, you sometimes don't want to have to type in all of these things every single time. So it's dead good if you can write yourself a function, and if you want to also pass to that function the most common variations that you're going to use in your work, then you can have a nice generic, easy to use 2 or 3 variable function which can then be interpret and draw your plots the way you want them. So if you're going to do lots of plots with small changes in the parameters, rather than do the whole thing every single time, create yourself a nice little function yourself that we can reuse. So again, we set that up as plot before. We're importing it, and we're not sure that's a good idea. We normally would try and do that outside of a function. Usually try and do it from higher up somewhere. So minimum value, maximum value, and so on. The print is also part of the function. The figure is also part of the function. The histogram, the whole thing is part of the function. And then we can just grab our column of grade and then call the function. There it is, down there. So we've defined that's the end of our function. The function includes this line here, tells you everything that's in the function. And as Richard would remind me, that means everything that's at the same level of indentation all the way up to there. So everything at the same level of indentation is all part of the function. There is no explicit undef or end function or anything like that. It's completely implicit based on how well indented it is. And then outside that indentation, therefore outside of that function, we declare our column variable is df students, which is our array, the grade column of that. And then we can call a function of just show our distribution, and we get the whole smash. Let's see. Now, I don't think it's wildly useful. Sorry, it did not run. Try again. I'll scroll down. Yeah. Oh, look at that. Nope, lost it again. No, it always does that to me. It goes right to the bottom. There we go. We see the whole thing. So we can look at our data, and we're pretty clear what's happening here. Is that is a very nicely behaved, quite centered data. There's a shape for that, which is called, I think, Gaussian, yeah, or normal distribution. It's applied, often called something called a bell curve as well in statistics, because it's shaped a bit like a bell, I suppose. So all the measurements of central tendency are right in the middle of the data distribution, with symmetric, with values being progressively lower on both sides from the middle. To explore this distribution in more detail, we need to understand statistics, which is fundamentally about taking samples of the data and using probability functions to extrapolate information about the full population of data. What does this mean? Well, samples refer to the data we have on hand, such as information about these 22 students' habits and grades. Population refers to all possible data we could collect, such as every student's grades. Usually we're interested in the population, but it's simply not practical to collect all that data. Instead, we try to estimate there is, from the small amount of data samples that we have. Now, there is another key word that comes along now called representative. Is your sample representative? If we have enough samples, we can calculate something called a probability density function, which estimates the distribution of grades for the full population. So based on our information we've got here and how the data distributes, we don't necessarily have to have a value for every possible grade. We can, using a probability distribution, we can predict what there should be, and this is where that's what the statistician did to the fisherman that wanted to find out how much fish he would catch next week, and the week after, because he was going to rent his boat out to someone else, and they were going to pay him based on the amount of fish they got caught. And the statistician asked him a few questions about what he'd caught in the past, on what particular day, under what sort of weather conditions, and then was able to do a probability density for what would have been missing in that time. So when the person would have had rented his boat in that time, so he would know how many he caught in the half of the time that he had the boat, and he should be able to then work out how much the other people caught in the times when he wasn't on the boat in those 2 weeks, and then they could pay the right amount of rental. So this is what this is about. This is about having a sample of actual data and being able to find out what would happen outside of the sample. So we are here, just above here. Keeps jumping. So we have enough samples, we can calculate the probability density, which estimates the distribution of grades for the full population. Data frame provides a helpful plot showing this density. So we're going to rewrite a new function called show density using var data, which was our did we create var underscore data? I think we must have. So import figures, yeah, same as usual. Now plot the density, add the titles, and put in our mean, median, and mode lines, and then plot it. And we'll see what we get. And there we go. So that is our probability density. The point being is the even though there are grades that don't exist, we can see from here what they should be for any. Most of our grades are around about 50 here. So as expected from the histogram of the sample, the density shows the characteristic bell curve, or what statisticians call a normal distribution, with the median and mode at the center and symmetric tails. So these are the symmetric tails. The median and mode at the center, you can see it's shaped a bit like a bell. And this normal distribution is absolutely everywhere. Every piece of data that you sample that's based on real kind of events over a range of samples, over a range of a population, invariably comes out as some kind of bell curve. Maybe shifted to the left or to the right, or maybe flattened slightly, but in general you get this bell curve for the data density. In terms of, now data density, remember, is all about how many samples are at that value. If there are a large number of samples at that value, then that will be the highest density. Okay, so there are a number of new concepts. So we've looked at mating graphs with matplotlib, seen how customize these graphs, calculate some basic stats, medians, etc. Looked at the spread, learned about samples and populations, estimated what a population of a graph might be from a sample of grades. In our next notebook, we'll look at spotting unusual data, so that's the outliers, and finding relationships between data, which, as we know, is things like regressions to find a relationship, don't we? So definitely advise you to get into those 3 things. And now we're going to move on to real world data. So have a read of that and you'll see what happens with outliers and so on and missing values.
Steve, I think you are on mute.
Oh dear. How long's that been on? So yeah, we're looking at the data distribution here. And as you can see, it's in the center. That's our mean there. It's not anything like as good as it was before. And this is a bit lumpy on this side here. And as you can see from the whisker plot, the whisker and box plot, that is nowhere near the middle of where all the data is. That's about where the middle of all the data is. So there's a bias to one side. There's a shift involved there. The whiskers only begin at around 6, indicating the vast majority of the first quarter of the data is above the value. Minimum is marked as a O, indicating that it's statistically an outlier. So let's have a look. Yeah, because it's way outside. This stuff here is way outside the rest of it. So this is how the system has indicated that this should be regarded as an outlier. Oh, and it's because I leave the mouse over the mute. That's why. Right. So we're going to get that variable to examine. We'll only get the students that have studied for more than 1 hour. So we're going to apply this mask. So our column is now the students in study hours, where study hours is greater than 1. And we can call that function, and we should it's slightly better behaved now, isn't it? Because what we're doing is we're making the assumption that a student that hasn't done any studying shouldn't really be part of the data set. So I don't know how often that applies at BCU. So we'll leave it there. For learning purposes, we just treated the one value as a true outlier and hence excluded it. In the real world, though, it should be usual to exclude data at the extremes. Unusual to exclude data at the extremes without more justification when our sample size is so small. This is because the smaller our sample size, the more likely it is the sampling is a bad representation of the whole population. So what might seem an outlier might actually, if you took a lot more samples, become the mainstream. And that does happen. The population means grades is not just our 22. For example, if we sampled time for another 1,000 students, we sample study time for another 1,000 students, we might find the actually quite common is to not study much. Yeah, so it all depends what your data is, whether or not your sample is representative of the population. When we have more, our sample becomes more reliable. This makes it easier to consider outliers as being values that fall below or above percentages. Pandas uses quartile function to include below the 10th, 100th percentile, the value of which over 99% of the data reside. So yeah, so that's quite a reasonable assumption to say that if it's not within 99% of all of the samples we've got, then you can be sure it's a reasonable assumption that it was in fact an outlier. So we calculate the 100th percentile, saying that Q01, which is the lowest 1%, is the study hours quantile 0.001. So that's a good label, Q01. And then we'll just make that the columns to be the study hours which are greater than Q01, and then call our function. So it's basically saying we picked a number, and it's the number where 99% of the values are above it. So that's the number. And we planted that into getting our students' hours that are quantified to that, and then using that as a mask to show our data. We've now got a minimum 6, maximum 16, and the median is starting to behave itself a little bit more. So we've now got rid of those lower values, the really silly lower values. You can also eliminate outliers at the upper end by defining a distribution at a high percentile value. For example, you would use the quantile function to find 0.99. As I say, in my calculations, I discarded the bottom 20 and the top 20 results when I was working out the grade boundaries. That's a bit extreme. You couldn't normally do that outside of a school situation. But with the outliers removed, the box plot shows all the data of the 4 quartiles within the 4 quartiles. Note that this distribution is not symmetric like it is for the grade. There are some students with very high study times, but the bulk of the data is between 7 and 13. The few extremely high values pull the mean towards the higher end of the scale. So look at this distribution then. And as you can see, it's not a bell curve. It is shifted, it is skewed over here, and the kind of distribution is called right skewed. Yeah, so it's skewed towards the right. There's much more in here than there is over here. The mass of the data on the left, this distribution is creating a long tail to the right because the values at the extreme high end pull the mean to the right. Okay, so we've got an incredibly long right hand tail, and so now we've got a good idea where the middle of the grade and study data distribution are. However, there's another aspect of a distribution we should examine. How much variability is there in the data? Now, statisticians love variability and variance. So let's get some terms. The range is the difference between the minimum and the maximum. There's no built-in function for this, but it's easy to calculate using the min and the max functions. Yeah. Variance is the average of the squared difference from the mean. You can use the built-in var function to find this. Let's think about this n. The average of the squared difference from the mean. So take your value and then find the square difference. So really that is looking at spread, a spread of the data around the average. And a standard deviation, which is the square root of the variance. And you can use this built-in STD function to find this. Very powerful idea, standard deviation. You can measure the variance of something within a certain number of standard deviations, and if you're comparing results, for example, if you're within a predefined number of standard deviations, then you can show that you're not varying too much from that point. So column name in grade study hours. So we're doing here. So for both the columns of grade and study hours, set the column is DF students column name, and then the range is the column max minus the column minimum. That makes sense. The range of values is the maximum minus the minimum. And then we can set our var to be colvar and our standard to be column standard deviation. So we should end up being able to print out the range, the variance, and the standard deviation for both the column name which are of type string. Okay, and it's going to apply it to both of these columns. So these two columns is done for this one, and then it's done for this one. Let's see what we get. So there we go. It's done for the first one. So that's for grade. And it's done for the second one, which is for study hours. Okay. We've got the range of variance and the standard deviation. And as we can see, on these statistics, the standard deviation is generally the most useful, provides a measure of variance in the data on the same scale as the data itself. So the grade points for the centigrade distribution and hours for the study hours distribution. The higher the standard deviation, the more variance there is when comparing values in the distribution to the distribution mean. In other words, the data is more spread out. So your standard deviation is about spread. When working with normal distribution, the standard deviation works with the particular characteristics of a normal distribution to provide an even greater insight. Run the cell below to see a relationship between standard deviation and the data. Watch this. So we're using Skippy for the statistical stuff. Grabbing the grade column as usual, setting the density. Now this is this Gaussian that I mentioned to you, representative of kernel density estimate using a Gaussian, which is the plot the density, get the mean and the standard deviation, annotate for one standard deviation, it's here. It's just basically a plot. Annotate two standard deviations and 3. So it just tells you what we get in what levels of variance, and then show the location. So let's have a quick look at that before we finish. I think this is going to look fantastic. Okay. There we go. So all of the students are within 3 standard deviations. 2 standard deviations captures 95, and 1 standard deviation captures 68.26 of the variance. So the horizontal line shines the percentage of data of the mean plus or minus in any normal distribution. Approximately the values fall within 1 standard deviation of the mean, fall between 2, and fall between 3. Since we know that the mean grade is 49.8, the standard deviation is 21.4, and the distribution of grades is approximately normal, we can calculate that 68.26% of students should achieve a grade of between 27 and 70.92. And it's this that enables you to set grade boundaries in exams based on what you want the number of students to be in each of the grades. The descriptive characteristics we use statistics we use to understand the distribution of student data are the basis of statistical analysis. And because it's an important part of exploring your data, there's a built-in describe method for the data frame objects that returns them. So there we go. We can just simply say df students describe, and it gives the whole smash. I'll need a new sandbox. And run again. That's nice and easy. And then once you get it, you can zoom in. It didn't run. Oh, it didn't do a plot function, did it? I don't think. Let's have a look. Let's see. Trace match run an error for some reason. Did I miss? Did I not run something? Oh, because oh no, we haven't got to run everything again because it's a new sandbox, have we? I think we have to. So we're running Skippy. DF students we don't have yet. When did we create DF students? The last time we did a get. That's it. So this is when we got we created everything when we last time we downloaded it. So we do that one. Taking a while. On that one, so we need to go down. So you had to go back as far as the last import. What a pain. Now, did this do anything? Cold DF, students, study hours, show distribution? No, that didn't do anything. No, that didn't add anything. Yes, it did. No, that didn't add anything. We didn't add anything there. Didn't add anything there. All there. All there. So let's see if this works. Hey, there it is. So we've got the count, the mean, the standard, the minimum, 25%, percentile. So that's it. So basically you can use those numbers there in Describe to pretty much do everything you want to do. Okay. Well, I saw you couldn't hear me for a while because I'm not going to do it anymore, but I keep my mouse arrow over the mute button for some reason, and it seems to activate itself. So, okay, so we'll be moving on next tomorrow to comparing data, comparing numeric and categorical variables. So let's come back tomorrow. We'll just save that as our starting point for tomorrow.
Steve,
Yep.
would you be able to give me a call after the class, or maybe
Sure.
I can stay online?
Yeah, just stay online. It's fine. Yeah.
Thank you.
Okay. Well, thank you, everyone. See you tomorrow.
Thank you. See ya.
Bye.
Thanks, bye.
Bye.
Sorry, Steve, I will just wait for everybody to leave.
Yeah, of course. That's fine. Thanks for coming today, Saeed.
Thank you. Yeah, so sorry about that. Steve, so how are you doing?
Yeah, I'm doing fine. How are you?
Yeah, good, thank you. So, I
Yeah,
have...
cheerio, Zaid.
Sorry?
Okay, we're on our own now. Zaid's gone. Yeah.
Yeah, so I have been applying for jobs.
Brilliant.
So I got one offer and they're asking for, their references.
Yeah.
So can we get references from BCU, like for playbooks or any, something like that?
Don't be at all concerned by it. I'll talk to Dr. Rice about it tomorrow.
Yeah.
And I'll be very, very delighted to write you a reference.
Thank you. So for the I'm a little bit lagging behind the Python part. I'll catch up because I was just preparing for the interviews.
No, it's fine. I don't have any doubts at all about your abilities to move into any of the data science roles that this course was designed for people to go to. And I think you'll do brilliantly wherever you go.
Thank you very much. And Steve, would you be able to give me your, I'll send you my, LinkedIn. If you can maybe leave some good reviews for me over there as well. I'll really appreciate that.
I'm not on LinkedIn, but I'll ask Dr. Rice to do it tomorrow.
Okay.
He can do all the good things that normally happen on social media.
Okay.
But you've got my staff email, haven't you?
I got the BCU one, yeah.
Yeah, that's fine. So
Okay.
yeah, by all means, use my. It's best to use my staff email, which is
Yeah.
StephenJacobs2.
Okay. Would you be able to?
Stephen.Jacobs2.
Okay. I'll just quickly note it down.
No, it's fine. Stephen.Jacobs2.
Yeah.
At bcu.
Yeah.
.ac.
Yeah.
.uk. Now I'll have to clear it with Dr. Rice tomorrow, but I'm sure he won't have an issue. And then whoever you need to have references from,
Yeah.
they can use that email to
Yeah.
to get me,
Okay.
and I'll be pleased to respond. I'll keep the university informed.
Yeah.
But yes, no, I think it's brilliant that you've got an offer. Is that where you want to go? Is it a company that you've been looking at, or is it local? And
yeah, it's local. So that's a big thing for me now. I want to stay local.
Don't tell them that. Don't tell them that that's the reason. Because I can tell you a joke. It's a really good joke. There's a guy. He goes for a job as a handyman.
Yeah.
And so the woman who's interviewing him says, "So can you do carpentry?" And he says, "No, I don't know anything about wood." He said, "What about a building? Are you a builder?" He says, "Oh, bricks and mortar? No, not me." He says, "Well, what about plumbing then? Can you do plumbing? Water, gas, and all of that?" He says, No, I don't do any of that. She says, "So how can you say you're a handyman?" He said, "Well, I only live around the corner." All right.
They don't feel like that. Yeah. So it's basically a Java role. So yeah. Yeah, I'll remember that. But I did tell them that this is really lovely and nearby. And earlier I used to drive 1.5 hours one way sometimes in the traffic jams.
I've done it.
Yeah.
So it's machine learning or data science with Java, yeah?
It's just Java, but they are looking into exploring it further. So they don't have any branch as yet. So it will be
Right.
They are not looking as such to invest in me for data science part of it. But I'm hoping that they once I settle in, I can ask, and they will let me play with the data and do something about it.
Yeah, it's an excellent way to start. If you're starting where nobody else has been there in a company before, you've got a real chance to make your mark in that. And if there's anything that we can do to help you in any way, then just ask.
Thank you.
We'll always be there.
Yeah, thank you very much. Yeah, I'll really appreciate that because there's no team there as yet. So hopefully I'll get good.
I think keep us informed even after you leave this course at the end of January. Just keep us informed about what you're doing and everything.
Sure.
We're always interested in that.
Sure. Thank you very much, Steve. Thank you for your time.
Okay, so I will check with Dr. Rice tomorrow if he's happy for me to be a reference, and if there's any kind of paperwork at this end for that. And there you go. So yeah, we'll do that.
Brilliant. Thank you very much.
I'll see you tomorrow.
Thank you. See you.
Bye.
Bye.